What do you understand by adsorption, by the way? And let me stop the recording also. Is a mass transfer operation. It means that the liquid phase, if there is some substance that accumulate on solid phase, so mass actually transfer from one phase, which is liquid or gas, to another phase, which is solid. So if we use this principle or operation, we can remove some contaminant which is present in liquid phase from liquid into solid, and we can eliminate it. But actually, there is no degradation of contaminant. So mass from one phase transferred to another phase and accumulate on the surface. So it is just transfer, mass transfer operation. Usually, this solid phase, we call it adsorbent. And whatever we want to remove, we call it adsorbate. So this adsorbate is accumulating on adsorbent. Generally, very commonly in water treatment, we use two different type of, actually one very common adsorbent, which is activated carbon. Activated carbon. It is commonly used adsorbent. And there are two type of activated carbon. One activated carbon is granular activated carbon, and another is powdered activated carbon. Both are activated carbon, but because of their size, the particle size, they are either granular, which is 0.5 to 3 millimeter, or powder, 20 to 50 micrometer. You can see here micrometer. So this granular activated carbon is a bit bigger than powder activated carbon. Otherwise, both are activated carbon, means both are carbon. So most commonly, we use the solid phase activated carbon for removal of different organic adsorbate. Did I talk this thing previously with you?
Yes, sir.
I did, right? Sir. Okay. So IUPAC, which is organization, has classified this pore size. Okay, if I mention, and here you can see some diagram of different magnification of pore size. This is 10 micrometer, is 30 micrometer. Here C is 100 and so on. So you can see the pore size here. This is the pore size of some activated carbon. When you continue to operate, when you do adsorption and you have adsorbate, which is solid material, and you continue to do adsorption, some time will reach when this adsorbent will become exhausted. Then what you have to do, either you have to regenerate or reactivate. The regeneration is something you don't change anything, just remove that attached molecule from the adsorbent. You just remove them, dissolve them, and in their original and modified state, with no change in carbon surface. Just try to remove by the changing pH or changing some other desorption chemical. However, this regeneration in water treatment carbon is very rarely practiced. So it's not practiced very commonly. The regeneration can be thermal, Can be physiochemical, can be biological, also can be, of course, chemical. But usually we don't regenerate at site. But if you are developing some adsorbent, you have to see regeneration, how to regenerate, how long it will take to regenerate, how much chemical or how much energy is needed to regenerate. You have to see this. But generally, we don't regenerate at site for water treatment. Another method is reactivation. Reactivation is actually restoration of the adsorption capacity through partial desorption of the solute molecule and then burn of carbonaceous residual. So you just try to remove some attached adsorbate on the surface, either thermal, physiochemical, biological, just like regeneration, and then burn again at 111 or degree centigrade or 800 to 111 1100 degrees centigrade to remove all carbonaceous residue. Both regeneration and reactivation usually we don't do for water treatment carbon, because water treated carbon is originally raw material originally is very cheap. So overall the value is very cheap. But for specialized purpose, we do this regeneration and reactivation, and we burn off again to reactivate the gag. We can do this, but usually we don't do this. Generally, we just throw away the carbon and buy new carbon and use it. But also in some application other than carbon, for example, is adsorbent in platinum or some other metal or some other thing, we send back the adsorbent to the manufacturer, and manufacturer they burn everything off, carbonation or residual material, whatever it is on adsorbent, and reactivate that adsorbent and send back to us. This happens usually in market. But for water treatment, generally, we don't use regeneration and reactivation. We just change the adsorbent because adsorbent is very cheap. Okay, did I talk about adsorbate water interaction, adsorbate surface interaction, and water surface interaction? Did I talk in the last semester? Three type of interaction. These interactions are called adsorbate water interaction, which is determined by solubility of adsorbate. Adsorbate and water interaction. So you know, if in water treatment, if we have water and we want to remove adsorbate using some adsorbent, which is solid material, suppose. So there are three things. One thing is water. Another thing is adsorbate. And another thing is adsorbent. So yeah, I cannot write today because I don't have pen. So we have interaction in between adsorbate water interaction, which is actually basically solubility of adsorbate, and adsorbate surface interaction, means adsorbate and adsorbent interaction, and which depend on surface chemistry of adsorbent, and also it determine what will how strong will be in affection of adsorbent and adsorbate, means how strong adsorption will be. And third one is water surface interaction. So water will also interact with adsorbent. It also depends on surface chemistry of adsorbent. So there are three type of interaction here. Important factor which involve in adsorption are We will discuss it, three of them, three interaction we are discussing actually, but the important factor which we should see are pore size of adsorbent or solid surface, and surface area of the adsorbent. So if we have a larger surface area, then we will have more sites available for adsorbent. If we have more pore size or smaller pore size, then we will have more uh, mm, surface area available, and then it is possible that more adsorption will be better. So number of adsorption site and the accessibility of the sites for adsorbent, both are important. And there is an inverse relationship between if pores are very small for a given volume, the surface area will be greater. As I mention usually, always 1 minute. Let me talk about the chemical adsorption. We also call it all chemisorption. In this kind of a reaction, a bond is formed. It can be covalent bond and or ionic bond between adsorbate and adsorbent. So this kind of reaction are very specific to a particular site or functional group. So adsorbate has some functional group, and if there are some more molecule present, different type of molecule, only that molecule or that adsorbent will react, which has some reaction mechanism, or which has potential to make covalent bond and ionic bond, and only here, not here, only with this. So this is chemical adsorption because the chemical reaction occurs. So chemical adsorption means the chemical bond is formed. It can be ionic or it can be covalent bond. These attractions which I mentioned to you earlier, they are not chemical bonding. There are some attraction and repulsion, weak interactions. Consider a water molecule. This is water molecule. Water molecule is a dipole also. Water molecule is dipole because I want to ask this question. So hydrogen is water is polar molecule. So it will induce dipole attraction, and it will have dipole attraction and repulsion. So if there is some positive charge will make bonding with the oxygen. If there is a negative charge make bonding with hydrogen. And this kind of bonding is not ionic bonding and not covalent bonding. We call this bonding hydrogen bonding. Is a very weak bonding. This is a special case of dipole-dipole interaction. For example, if you see here, water molecule, another water molecule which has oxygen will have some kind of attraction with hydrogen, weak attraction. We call it hydrogen bonding. And also, if you see here, like this molecule, ammonia and ammonia, because nitrogen has more power to attract electron and has more, so electron will have more circulating around nitrogen, so it will have negative charge, slightly negative charge as compared to hydrogen, and therefore they will be able to make hydrogen bonding. This hydrogen bonding is very useful for different type of solution. I mean, water itself is a universal solution solvent, It is because of this polarity and also hydrogen bonding. And hydrogen bonding also define the boiling point of water and so on. So it is important, but this kind of bonding is not that important uh, in water, because water interaction, this bonding is more strong and more abundant as compared to any surface has can have any bonding with adsorbent. If this is adsorbate and this one is adsorbent, they may have hydrogen bonding, but because water is present and water is too much present, I mean water quantity is too much in water because we are doing water treatment. Because of this reason, this is not that important in water treatment, this kind of hydrogen bonding because of water. So the functional group which are present on the surface, this functional group, which make interaction with the adsorbate, uh, they can be many. There can be alcohol, ether, LDR. There are functional group, and you can induce any functional group on your adsorbent, which can interact with adsorbate. So these functional groups, suppose there is a functional group. There is a functional group which is negatively charged, and there is a adsorbate which is polar adsorbate. So ideally, there should be interaction between this negatively charged adsorbent and the positive end of polar adsorbate. There should be some interaction, right? But this interaction is not that significant because of water. The water will interact first with this polar or charged species, because of the concentration of water in water solution in water is 55.5 moles per liter. It is very high as compared to concentration of adsorbent, which is in our case or our perspective is a contaminant we want to remove, is already very low. So because of this reason, this interaction is not that significant as compared to the interaction of water with this uh, functional group, because water has high concentration. If you calculate the concentration of water in water, then you will consider, you will calculate it 55.5 moles per liter. Is very, very high. So because of the higher concentration of water is more polar than most adsorbate. This interaction will be more significant, and there will be no adsorption. So you have to understand this, especially for charged functional groups. And also you have to understand that whatever, I mean, if water is making any interaction with the functional group, there will be no adsorption because the concentration is quite high of water. Concentration of water is very high. Do you understand this point? Okay. What about if functional group is oxygen containing functional group? If oxygen containing functional group is there, oxygen containing functional group is something like this one or this one. You see all of them, they are oxygen containing functional group. This one, this one, this one, this one, or like this one. If any functional group has extra electron, it will be polar. An oxygen containing functional group will be polar. So if oxygen containing functional group is present on the surface, it will reduce the activated carbon capacity because it is polar. So it is polar, it will attract water quickly. So oxygen containing functional group is present in water. will, on the surface of adsorbent will reduce the capacity of adsorb, adsorb, adsorbent because it attracts water and charge species from water to adsorption site. However, oxygen containing functional group, if present on adsorbent, it can make complex with heavy metal. So if you are developing some adsorbent which has oxygen containing functional group, it may react with heavy metal. Heavy metal. So you want to remove heavy metal using adsorbent which has oxygen containing functional group, and also it can remove hydrogen sulfide or phenol or natural organic matter also. Okay. What about neutral molecule? If you want to remove neutral molecule from water, then you have to consider London van der Waals forces or simple van der Waals forces, which are related to polarizability of adsorbate and the adsorbent. So if you have certain, like you can see here, if you have certain functional group which is positive, which has two polar, means positive charge has positive charge and negative charge also, and you want to remove a neutral uh, adsorbate, then what happened? This, because of this charge, there will be slightly polarizability. We call induced polarizability because it is induced because of this functional group dipole functional group, and there will be some interaction between this because this is induced by this. So water molecule will not do, because this adsorbent will come close to this one. Then there will be some polarizability, and then interaction will occur, and then molecule will attach with the functional group. It will happen both in case of dipole or if there is a charge species there, because both charge species and dipole will induce polarizability will induce polarity in neutral molecule, and neutral molecule will attach. But anyway, uh, this is not that strong. This kind of interaction also are not that strong, and overall are not that significant because of anyway pore water is there. So as I was mentioning, there was chemical adsorption, one type of chemical adsorption. But because of this reaction which I mentioned to you, the weak physical forces, the adsorption is occur. We call it physical adsorption, and this physical adsorption are because of physical forces, not covalent force bonding, not Coulombic attraction or ionic attraction. So uh, the other under van der Waals force or hydrogen bonding or some other forces are responsible for physical adsorption, and as in contrast to chemical reaction, this kind of interaction are less specific, weaker, has weak energy of bonding, and operate over longer distance. So if you have uh, reaction, reaction will operate over longer distance as compared to chemical reaction, and these are reversible. I think we discussed it earlier also. So if you want to remove organic adsorbate from water on non-polar adsorbent, so if you have adsorbent which is non-polar and you want to remove organic adsorbent which is also not polar, so in this case you have to consider, let's suppose we are using activated carbon, and activated carbon is cross-linked graphite crystalline plane. This is like this. So it form micropores. In this case, the major force of responsible force is van der Waals force, and van der Waals force will have some effect of accumulation of organic neutral molecule onto activated carbon, which is also neutral, this is non-polar. So the important thing is here, because this is neutral, then it is not soluble in water. So if it's not soluble in water, it will have affinity on solid surface, which is also not polar. So the adsorbate, which are less polar and have low solubility, will be attracted toward adsorbent, because the interaction or attraction between adsorbate and polar solvent, which is in our case water, will be weaker, because adsorbate is less polar or non-polar, so solubility is low. In this case, this adsorbate will be attracted toward non-polar adsorbent, which is in our case, which our example is activated carbon. So, and so the attraction between adsorbent, less polar adsorbent or neutral adsorbent and activated carbon are because of van der Waals force, and this attraction increase with increasing in polarability and size. Suppose if you have a methane molecule and neon, the atomic weight of neon and methane molecule is the same. Both have 8 electrons in their valence shell, but methane is the orientation of methane is so much so that the size of methane is bigger than neon. It's because of the not uniformity in orientation. Is a tetrahedral structure as compared to this one, which is all homogeneous structure. So because of this structure, although they have similar number of electrons, the size is different. The size is increased, then it is possible that the polarity will increase also. And the polarity will increase, then its interaction of with the water will be less. Interaction with the adsorbent will be more. So more non-polar and large molecule tend to adsorb more strongly to non-polar adsorbent, in our case activated carbon, using hydrophobic bonding, because they are hydrophobic, so they will attach to non-polar activated carbon. Okay. The examples are, what I mentioned to you, are here. If you see the concentration here and the adsorbed acid, if you increase the concentration and you see the adsorbed acid, and the cases here are formic acid, acetic acid, propionic acid, and butyric acid. Okay. You know the acetic acid, the formula of formic acid is HCOOH. This is formic acid. And acetic acid is CH3COOH. And propionic acid is CH3CH2COOH. And butyric acid is CH3CH2CH2COOH. If you see, the formic acid has the smallest size as compared to acetic acid, and acetic acid is smaller than propionic acid, and propionic acid is smaller than butyric acid. So if you see the size, the adsorption is increasing as size is increasing. So butyric acid has more adsorption as compared to all three of them because the size of butyric acid is larger. So more non-polar and large molecule tend to adsorb more strongly than non-polar adsorbent, which is clear from this example. This is not a very good example, but anyway, gives one clear picture. So if we have activated carbon and we have different class of uh, class A, class B, class C, some are polar, some are non-polar, and then some physical forces are responsible. Which physical forces will be responsible for what class of chemical? How we know this? We know one thing, that non-polar and large molecule tend to adsorb more strongly to non-polar adsorbent. But how we know that which force is responsible and what type of chemical will be attracted, whether class 1 will be attracted to an adsorbent or class 2, or which one will be more stronger? It is difficult to say, but we can have certain key points, because we cannot measure these forces and interactions which are responsible for attraction. We cannot measure quickly. So we have to see properties of adsorbent and solvent, which is water. For example, the solubility. So we have to see solubility. Solubility we can measure easily. Physically we can measure. So we can have one key point. Low solubility of adsorbate, higher will be adsorption. This is one thing we have to consider. As much the adsorbate has low solubility, it will have higher adsorption on granular activated carbon. But this is not only one indicator, there are more indicators. This is a major one. You have to see the solubility. Okay, see the different compound like polar species. If there is a polar species in water, which I think one of the question was like this also. So interaction with polar species with adsorbent will be weaker as compared to the polar species will have interaction with water. It will be more stronger. So because of this, it will be soluble, and then there will be no adsorption. So because of strong water adsorbent forces and strong adsorbent water interaction, this kind of polar molecule will not adsorb on neutral adsorbent. Like, however, it depends on pH also. So if you see, in case of acid, if you dissolve acid, put acid HCl hydrochloric acid in water, it will form hydrogen ion and chloride ion. But depend on acid pH, the reaction may tend to this side. So the molecule of HCl may be undissociated form at pH at very high pH. And at very low pH, because the concentration is higher, so reaction will toward this side, and you will have undissociated forms of acid. So if it is undissociated form of acid, then reaction is possible now with neutral adsorbent. So also depend on pH as well. If you want to remove neutral species strongly hold the non-polar surface like activated carbon. So polar species are difficult to remove, but depend on pH, and neutral species, they will be quickly adsorb on or have tendency to adsorb to be absorbed on activated carbon. So what you have to see also, you have to see the solubility, the adsorbent water interaction, and you have to see the polarizability, adsorbent interaction. This polarizability depend on the size of organic compound. As size is increasing, it is possible the increased size will induce more polarizability on the molecule, and molecule can then have interaction with that adsorbent. In case of adsorbent interaction, you have to also see how many water molecules must be pulled away from the surface of the adsorbent, and how many water molecules must be removed from the surface of the adsorbent. So when you want to do adsorption, there are already certain water molecule present on surface. They may be attached on the surface. So this adsorption should remove this water molecule out, and then adsorption will occur. So if adsorbate is the neutral organic species, we have to see the solubility in water. If solubility is less, then adsorption will be more. We have to see the polarizability of the compound, which depend on the size of organic compound. If size is larger, the adsorption will be more. If polarizability of the compound is with its size is larger, also the adsorption will be more. And there should be no interaction or less interaction between water and adsorbent. So with these conditions, this factor we have to consider, then we can decide whether this adsorbate will absorb or not. This if it is organic compound. Now I'm talking about organic compound, not talking about any complex. Is remember, heavy metal can make complex with activated carbon. Okay, let's talk about ionic species. Adsorption of ionic inorganic onto inorganic adsorbent. Consider some surface which has hydroxide site on metal oxide adsorbent. So the adsorbent is metal oxide, which has hydroxyl on the surface. And consider metal ions, which is in the form of metal hydroxide. So there will be, in this kind of adsorption, there will be exchange of metal. So metal will come here, and this hydrogen and this hydroxide will form water. So in this way, the metal will be attached on the surface. This adsorption will happen, and metal can be removed from water. Examples are adsorption onto silicon, aluminum oxide based clay, and sand. If we use this kind of adsorbent, we can remove heavy metal. Adsorption of ionic species to the surface depend on electrostatic attraction and also pH and ionic strength. Anyway, when you want to remove heavy metal, you have to use metal oxide adsorbent, which has hydroxide site which hydroxide can be attached with this one, and together water will form. Metal will attach on the surface then. Can you hear me?
Yes, sir.
Yes, sir.
Okay, so this is all theoretical background, which we can see what class of compound, whether it's ionic species, neutral species, or heavy metals will be attached or not. What we have to see, these things. Solubility in water, polarizability, size of organic compound, and reaction of adsorbent with water. We have to see this, consider this, then we can see, we can decide this organic species can be removed or not. If it is ionic species, then we, what kind of adsorbent is there, must have hydroxide side. These reactions anyways depend on pH and ionic strength. So I stop here. We will continue to talk adsorbent, equilibrium, isotherm. Did I talk these isotherms earlier?
Yes, sir.
Yes, sir.
Really?
Yes, sir.
Did I talk about Lagmore isotherm?
Yes,
Yes,
sir.
sir.
Okay, then what about Friendly's isotherm?
Yes, sir.
Did we solve this example also? I think we solved. If
Sir.
I talked, I remember.
Yes, sir.
Yes, sir.
Okay, then I don't know. Did I talk about powder activated carbon jar test?
No, sir.
Okay, then I will continue from here. I will skip the models like more and Friendly, but you may consider those models. It is part of your course. Okay? And then we will continue to talk more about adsorption. And did I talk about application of powder activated carbon?
No, sir.
Okay. Okay, then we will solve some problems, and then we will control. Hopefully, by next in next class we will finish our